Posso partire? Okay. Okay, good morning, everyone. Welcome to the second day of the main conference. And today the conference will start with our keynote speaker, Professor Leal-Taixe. She's a tenure-track professor at the Technical University of Munich, leading the Dynamic Vision and Learning Group. Before that, she spent 2 years as a postdoctoral researcher at ETH Zurich and a year as a postdoctoral research in computer vision group at the Technical University in Munich. She obtained her PhD from the Institute of Information Processing of the Leibniz University of Hanover in Germany, spending a year as a visiting scholar at the University of Michigan. She pursued a bachelor and master degree in telecommunication engineering at the Technical University of Catalonia in her native city of Barcelona. She went to Boston, USA, to do her master thesis at Northeastern University with a fellowship from the Vodafone Foundation. She is a recipient of the Sofia Kovalevskaya Award of 1.65 million euros for her project Social Map. Her talk is entitled Shift Paradigms in Multi-Object Tracking.
Thank you. Thanks for the kind introduction. So sorry for the delay. So I have this very weird thing that I want my fonts to be special. So I prepared this whole presentation with special fonts. But when we moved to this computer, it didn't work. So if you don't like the fonts, don't blame me. So yeah, today I wanted to talk about, so I was thinking which topic to present among the research that we're doing in my group. And I was thinking, well, I've been working for quite a long time in multi-object tracking, so I can present a bit like the history, right? Like the last 10 years of multi-object tracking, which seems like a lot. But then yesterday, Roberto came in and said, I'm gonna do 30 years of computer vision. So, okay, well, I have only 10 years to present to you, but I hope that's gonna be fun enough. So yeah, the task of multi-object tracking, pretty straightforward. So we're looking at detecting and tracking all the objects in the scene. In my case, we have been working quite a lot on pedestrian tracking. I find tracking pedestrians is actually very interesting because they move quite freely, right? They have the will to go anywhere. They don't have static motion or, let's say, rigid motion that sometimes cars have, that they have to stick to a lane. So it's very interesting to analyze things with people. And of course, it's also quite, you have a lot of applications, right? So think autonomous driving, not to run over a pedestrian. You really have to know where they all are, how they are walking around. Also for augmented reality, for example, you need to interact with the dynamic scene. And for this, you really need to know where every object is. And quite interestingly, we have been working a lot on this task for the last years, but we have also made a lot of progress, right? So when we opened Mod Challenge back in 2014, our idea was to put together all the sequences that we had for multi-object tracking that people were using here and there in the community, put them all together and create this benchmark. And these were the type of sequences that we were using, right? So like we had these 5 people walking around, and this was crazy difficult back at the time. Now it seems really, really ridiculous. But for example, when people went behind this pole, then you could not track them anymore, or we had this very famous false positive for the tripod of the camera that was always detected as a person. So there were the kind of challenges that we had back in 2014. So fast forward, 2016-17, we said, well, we need to really kickstart the community, right? We need to pick some sequences which are harder. We need to motivate people to work harder on this problem. So we opened the 16-17 benchmark, which, as you can see, is a bit higher resolution. We have much more accurate annotations, more crowded scenes. Also, occluders are annotated. So we tried to provide this new level of difficulty so that people could work on this problem and make a step forward. And last but not least, a couple of years ago, we released Mod 20, which is this completely crazy scene, right? There's tons of people walking around. Just to annotate these sequences, we went completely crazy. It was super hard to annotate these sequences. And people have been really working on it and have been really pushing the accuracy also on these sequences. So you can see here how much progress we have made in terms of the difficulty of the scene, also the quality of the annotations, the quality of the image, and therefore the information that you can get from it. So when preparing this presentation, I was inspired by a student of mine, actually, that I'm teaching this course, Detection, Segmentation, and Tracking. And there comes this student and says, well, you know, multi-object tracking is very boring. And I'm like, well, thanks, man. I mean, I've been working on it for the last 10 years. And I'm like, okay, why do you think this is boring, right? And he said, well, there's no deep learning. And I was like, okay, well, first of all, that's not true, right? I mean, this first lecture, I just started with the basis. So we will get to the deep learning part. But for him, like, no deep learning, no end-to-end learning was completely boring, like not really worth studying. So I said, okay, I'm going to do a presentation where I follow basically the same structure, right? So I go from the non-deep learning type of doing tracking, which is tracking by detection, and I will slowly move towards new paradigms of tracking that have appeared in the literature, like, for example, tracking by regression, which is already a big deep learning, more deep learning-ish, all the way to what I think and hope will become the new paradigm, which is tracking by attention. And this goes from treating tracking in a separate way between detection and data association. So it starts at that point and then moves towards unifying detection and data association, and also moves towards obtaining a more end-to-end solution to tracking. And at the end, I will present what I think is next for the tracking community, right? So what are the interesting problems that we can still work on? So hopefully this presentation will go from the boring part all the way to the fun part. Okay, so let's get started. So what is tracking by detection? So this is still a very much used paradigm, so I have to say that it's not completely dead, and we are, even in my group, we're still working on it because it has proven really, really powerful. And the idea of tracking by detection is that you basically separate the problem into two parts. So analyzing a full video is very, very hard. I mean, you have tons of pixels that are coming at you, and you want to obtain trajectories from them. And so in order to simplify the problem, people said, okay, how about we separate the problem into two parts? First, we do the detection. So basically, we apply a detector on each frame of the video. And as a second part, we will do the data association. So we will actually look at all of these detections and create trajectories. So of course, this is easy if you're looking, for example, at the blue trajectory. We have all detections. We just need to link them. They are close by. Perfect. We start having problems when we have false positive or false negatives, when we have occlusions, basically. So these are the hard parts that the tracking community has to deal with. So this is a bit of a historic view that we did last year on all the methods that submitted the results on the Mod Challenge benchmark. So we can see here the 3 challenges and a bit of the evolution of the type of research that people are performing to solve tracking. So we start back in 2015, so on the left part of these graphs, and we see these orange blobs, which represent all the works that are using motion models. So back in the day, people were trying to replicate how people moved around the scene with physics-based models, with learning-based models. So a lot of attention was placed on extracting the motion of these pedestrians. That people moved more onto the purple blobs, which are the data association. So people started creating these huge optimization problems that they wanted to solve to obtain trajectories. And they were more and more complex, they had more and more advanced features. But the most important thing here to note is that they were getting increasingly complex. So solving these problems was taking forever just to obtain trajectories on one sequence. And then you have other methods, like, for example, working on appearance models or other types of handcrafted ways of doing tracking. Okay, so in order to move to the next paradigm, we need to take a look at each of these steps of the first paradigm that people have been using, right? This is why this paradigm is so famous. So we decided to take a look at both parts of the tracking by detection paradigm. First the detections and then the data association. What can we do in each of these two parts in order to improve tracking? So let's start with the object detection. So of course, back in the day, people were using maybe like hog detectors with SVM on top and so on and so forth. But detectors have really moved forward. And the tracking community was just using these detectors, right? It was not really taking more advantage of these detectors for the task of tracking. So this is what we tried to do. We said, okay, let's look at regression-based detectors. So probably you're all familiar with the RCNN family. So in this case, we were looking at faster RCNN, which was a very popular detector at the time. And we said, okay, let's see how this actually works and if we can take advantage of this detector for tracking. So this detector, what it does is it takes an input image, processes it with a CNN, and obtains a feature representation of this image. Now, of course, we're not interested in the whole image. We're just interested in the areas where we can potentially have an object. And this is why we have this concept called region proposal that tells us, look, this part of the image is interesting. Let's analyze it. Let's see if there's an object in there. So this is what it does. And what you can essentially do is go into your feature representation and grab the features that represent this region proposal. And from there, you can do many things. You can classify this proposal. Is this a car or a person or a cat? And you can also, you have this regression head, which what it does is it takes your region proposal and it nicely fits it into the object. Because as you will know, we have this accuracy measure for object detectors that want these super nicely tight bounding boxes. And it turns out that if you have this regression head, you improve your accuracy. So something that was completely, just to increase accuracy, it turns out it's going to be super interesting for us for multi-object tracking. So let's see how the regression head works. So if you have this region proposal, which I've now moved a little bit, right? So this was the actual output that we want to have. But it turns out that your region proposal is not perfectly placed on the object. It can happen. What this regression head does is it takes this bounding box and it tightly fits it around the object. So now this is going to be your output. Of course, the overlap with the ground truth is going to be much higher and you're going to obtain a higher accuracy. Nonetheless, the step of going from this region proposal to this region proposal can be repurposed for tracking. So let's see how this is done. So the inspiration came when we actually look at online tracking methods. So online tracking means that you're given frame by frame, and you have to track objects in real time, kind of in this frame by frame fashion. So you're not looking in the future, you're not looking backwards, you're just doing frame by frame. And in this frame by frame tracking, what you're doing is you're moving the bounding box from one frame to the other, trying to follow the object. And we thought, well, this is very similar to what this regression head is already doing. So we said, okay, how about we train this detector, but we use it for tracking. And this is how this name tractor was created. And the idea is that, let's say we find ourselves in frame t+1. Let's say we have already tracked these three objects for a few frames. And now we take, as proposals for our object detector, we take the detections of frame t, of the previous frame, right? So these are detections that are already color-coded because I know these detections carry an ID, but they are slightly moved, right? Because, of course, the person has moved forward, and so the bounding box is not perfectly tied onto the actual pedestrian. But now we know that we have this great, super well-trained bounding box regression head that is able to actually do the exact task that we want, right? It's able to take these boxes that were misplaced because they are from the previous frame, and it snaps them onto the pedestrian. So suddenly, without training our detector, without doing pretty much anything, we have a tracking result. But now you're going to ask, wait, I mean, I've just regressed a bunch of boxes. Is this really tracking, right? Can we actually say that you are performing tracking? So for this, we need to answer only one question, right? We need to answer where did the detection with ID1, for example, the red detection, where did the red detection go in the next frame? Can I answer this question? If I can answer this question positively, then I have performed tracking. So indeed, I know that the red box at frame T was regressed to that red box on the right, right? I know that this comes from the red box. I know which box regressed to which other box, which means that I have an implicit correspondence. And correspondence is the basis for tracking. So indeed, I can say, I can do the association between these boxes, that's why they're color-coded, which means that I can actually solve the tracking task for these two frames. So, okay, now you said, well, you did nothing, right? I mean, that's true. We didn't even train anything. How can this work so well, or does this work so well, right? So let's look at the advantages of this method. Well, FastRCNN was an extremely well-trained method. It was trained on a bunch of data. So we know that the regressor is going to be very accurate, very powerful regressor that works on multiple types of scenarios. So we automatically get well-positioned bounding boxes. So this is great. Furthermore, if now you want to do, for example, cell tracking, and there is no detector that has been trained for your specific type of cells, you only need image annotations to train this tracker, right? So beforehand, you will need to take long sequences, annotate each frame of the sequences, so on and so forth, very tedious. Now what you can do is annotate some still images and train FastRCNN on top. That's it. You have a detector and you have a tracker. And furthermore, of course, a tracker is online, which means that given the right backbone, you can use it for real-time applications, right? You don't need to look into the future, into the past. At every frame, it's going to give you a solution. So let's look at the disadvantages, right? This is an extremely simple model, so it has to have some disadvantage. And indeed, the major disadvantage for me is that there is actually no notion of identity in the model, right? So if I have a bounding box that is floating around, it will snap to the nearest object, whatever that object is. If it's the same object as the previous frame or not, it doesn't really care. It just snaps to the nearest object. Which means that in crowded spaces, you are going to have some confusion. So you are going to have boxes that are snapped into other pedestrians, and then you have identity switches. The other disadvantage is, as any online tracker, if the target becomes occluded, the box doesn't know where to go. It doesn't know where to snap, and you just finish the trajectory. So you need some method to close these small gaps and occlusions. Now, thankfully, people in the tracking community have already been using methods to solve these kind of problems. And these are re-identification methods, so methods that take two bounding boxes and tell you whether these are the same object or not. So you can very easily use this to solve these two problems. So not major problems, problems that can still be solved. Let's look at the third problem. So it turns out that this regressor is really well trained, but it's only well trained to shift the box by a small quantity. So as soon as your bounding box moves by a lot and you need to regress it more than just a tiny bit, then it doesn't work anymore. And we tried forever to train this regressor to shift larger amounts, but it didn't really work. It doesn't really converge. So we had to do something when we had, for example, large camera motions, right? When the camera moves a lot, the pedestrian also moves a lot in pixel space, which means that your regressor is going to lose the identity. Or, for example, low frame rate. If you have low frame rate, then the person is moving, but since you're taking less snapshots per second, the person seems to be moving faster in the video. So it can also be that if the person moves really fast, then your regressor also misses it. Now for this, and together with the second problem, people in tracking have also been using kind of techniques to solve these problems. And these are the motion models that I talked about initially. So very simply, one could use the constant velocity assumption, one could use a Kalman filter, any type of motion model that you want will actually tackle the last two problems. So it turns out that with very little work, with techniques that people were already using in their trackers, we can solve the major problems of this extremely simple tractor. Now, the most interesting part of the paper, I think, was not actually proposing a simple tracker, but was analyzing a bit the results of all the other trackers, right? Because if I can come with a super simple tracker and beat all state-of-the-art, then I want to know what all state-of-the-art are doing, right? I mean, what has been happening? What are the cases that state-of-the-art cannot solve and I can solve? So one of the results, one of the most interesting results, is this one where I'm plotting in the x-axis the bounding box visibility of the boxes in my benchmark. And on the y-axis, the percentage of tracked bounding boxes. So the first thing that we're going to see is that if the visibility is high on the right side, the percentage of tracked bounding boxes is also really high. These are all the easy cases where you see the pedestrian, it's nicely visible, and you can easily track it. On the left side, you see the hard part, where basically no tracker is really working, where you have 100% invisibility, so the object is completely occluded, and you basically have to hallucinate where the object is going behind the occlusion. Now, in these thick bars on the background, I'm plotting the distribution of occurrences in the ground truth, just to show you that most of the boxes have actually 100% visibility. So many cases in the mod challenge benchmark are actually super easy, right? Which means that everyone should be fighting for all the other cases that no one is really solving. But it turns out that this is not really the case. So we compare several methods which were popular back in the day. Some methods are online, some methods are offline, looking even at future frames. And we have two versions of our method, one with re-ID and motion and the other one without. And the interesting thing is this part in the middle, right? The part between 25% visibility and 75%, where we see that all the methods are kind of crashing. Their accuracy is really crashing. But our method is surviving quite nicely. So this is really the range in which we improve things. Now, the sad thing is that there are not many occurrences of this, in this range of visibility, right? So there are not many examples in which we can actually improve. And the other interesting thing is that even if you have methods that are doing tracking by detection, and they are creating this huge graph that looks at past frames, future frames, you look at everything in the video, so you think, oh, it's going to be able to recover from occlusions, right, because it's looking at the future. Well, it turns out that's not true. So it's really hard to recover from an occlusion, even a partial occlusion, even if you're looking into future frames, because you risk creating all these trajectories which are actually not true. So what we actually found out in the paper is that the really hard problems in tracking were still left unsolved, right? So, for example, covering large gaps in detections where you have large gaps in which you have no image evidence where the pedestrian is. It's really hard to cover these gaps and hallucinate the trajectory. Even recovering from partial occlusions is hard. And of course, tracking of small targets, right? If you have no detections, then you're not going to have any chance at recovering trajectories. And all the methods are kind of just fighting for these easy scenes, right? These scenes between 80 and 100% visibility, kind of fighting in there to improve on those scenes. And this is why, you know, between 2017 and 19, we only had this very tiny increase of 2.4 percentage points in accuracy in tracking. So in 2 years, this is not really much, right? I mean, now we're complaining when a paper only improved 2 percentage points in one go, but imagine in 2 years. And this is because everyone is kind of fighting for these easy scenes and no one is looking at the really hard problems. And it is partially our fault, the creators of Mod Challenge fault, because we don't have many examples in that range. Which means that if you improve on those examples, then you get maybe only a 0.1 percentage point increase. So people are not really motivated to work on these problems, right? So it's a problem of challenge, it's a problem of metrics. So it's a problem that we all need to deal with. So yeah, our work together also with CenterTrack and all the works that kind of spawned after this created this new paradigm, which I like to call tracking by regression. So we're shifting away from tracking by detection, where we split these two tasks in detection and data association. And we're going more towards merging these two tasks. In our case, using a bounding box regressor of a detector. In the case of CenterTrack, regressing center points from one frame to the next. And the major characteristic of these two trackers, or all the trackers that are using tracking by regression, is that the spatial cues are going to have much more importance than the appearance cues. So we're shifting a bit away from using appearance models, from really detecting a person's appearance and trying to find this person everywhere in the image. Okay, so as I said, this spawned a few works, right, that kind of were inspired by CenterTrack, by Tractor. And so all these works were created, these stars, are methods that are actually using tracking by regression. And you can see how the accuracy is really improved by using this new paradigm. So people are inspired, people are working on it, and keep improving the accuracy on mod challenge. So this was really nice to see. But of course, we wanted to move forward, right? We said, okay, we have solved all the easy scenes, right? Like the small occlusions, all these easy scenes that I've been talking about, they are solved. We can use Tractor for that. And tracking should really focus on the harder cases. So the long occlusions or the extremely crowded scenes where Tractor or CenterTrack are going to get confused. Okay, so how do we move forward, right? I mean, now it's time to tackle actually these problems. And for this, we need to look back at the tracking by detection paradigm, right? So I've covered object detector. So we have done as much as we can with the object detector. Is there anything we can do? Is there anything we can improve on the data association side? So let's take another look at data association. So I'm not going to spend too much time on this paper because I want to jump onto the third paradigm, but I just want to briefly present the idea behind it. So back in the day, so this is a paper from 2008, they were working on graph-based association. And graph-based association is offline, which means that you're looking at past and future frames. And it's not that it's useless, right? Like something that is not real-time or online is not useless. You can still use it, for example, for labeling, because you have, of course, more robustness compared to online tracking. And how graph-based association works is you first run your detector, then you construct a graph in which your nodes represent your detections. And then what you want to do is you want to solve this graph so that the edges that you get as a solution are edges that represent trajectories, right? So an active edge that connects two detections means that these two detections are actually belonging to the same person, to the same pedestrian. And therefore, they form a trajectory. So trajectories are represented by active edges in the graph. So, of course, this is a very sort of separate way of doing tracking, right? This whole pipeline of graph-based association is not end-to-end by any means. So you first have a feature extraction step, right? You have to put some information in the nodes and some information in the edges so that when you solve this problem, you obtain the right trajectories. And people spend, you know, countless papers into putting more meaningful information in there. And then you have some sort of discrete optimization on top. It can be simple, like a linear program. It can be more complex, like a quadratic program, if you actually want to put more edges in there. But still, these two steps, feature extraction and optimization, are still sort of separate. So what we would like to do is, first of all, we would like to start infusing some learning in it. And one super simple way of doing is in the feature extraction side, right? So you can simply use a CNN to extract your features to tell you which boxes are similar, which boxes are not. Kind of similar to re-ID, but infusing all this information into edges. This is kind of easy. But what we would really like to do is we would like to solve this in one go, right? To fuse this feature extraction and optimization and do it in an end-to-end learning fashion while we're at it. So what we came up with was what we call our neural solver. So essentially what we're doing is we're constructing a graph where we have these, you can see these tiny CNNs that are infusing information from the image to our nodes. And then we have what is called a neural message passing network. So this is essentially a graph neural network. And the cool thing about this is that now you can do learning on the graph space, right? So the structure of your problem is not an image. You cannot use a CNN. The structure of your problem is actually a graph. And I want to do learning on the graph. And this is why we have graph neural networks or this neural message passing. So the cool thing now is that you can pose the whole tracking problem as an edge classification problem. So a yes or no problem. Do I want this edge to be in my solution or not? And so the nice thing is that now I'm going to have the feature extraction, which is going to take place with the CNN, a learnable data association, but the coolest thing is what happens below. You can do backpropagation from the edge classification all the way to the image. Not that we did it in this paper, because this was super expensive a couple of years ago, but nowadays, with a bit bigger GPUs, this is totally doable. And this is really cool, right? Because now I'm actually doing feature extraction for the actual structure of the problem, which is the graph problem. And so I'm going to obtain better features, and I'm going to avoid the optimization that happens because I have to find these active edges. So as I said, we can directly work on the multi-object tracking domain, right? We're doing learning on this domain. We're learning these specific features for the actual problem, and we avoid the expensive optimization at test time. So the finding trajectories is just an edge classification, so basically you just need to do a forward pass through this neural message passing, and you directly obtain your solution. Okay, so what are the bad parts of this method? So if I do data association with graph neural networks, I can really resolve partial occlusions. So it's really good at that. And crowded scenes are handled rather well, right? I mean, you're looking at all the pedestrians in a batch of frames. You're trying to resolve all the trajectories at the same time, which means you're going to have quite some robustness in crowded scenes. The problem, though, are still the long gaps. So in order to solve long gaps, I would need to have this huge graph that connects basically all detections with all detections. Because if I have a gap in detections, it means that I have no nodes for, I don't know, 100 frames. And then I need to have an edge that goes from the first frame to the 101th frame. I need to connect these detections somehow. So having this huge graph and learning on them is not really feasible. And at the same time, we're kind of still relying on these detections, right? I mean, we're still doing tracking by detections. And I promised at the beginning that I would throw away tracking by detection and move on to a new paradigm, right? And I can still not do that. So end-to-end learning is still not possible with this paradigm. So the last paradigm that I think is, of course, the most powerful one and also the most fun one, at least for my student, is the one that unifies detection and association. So finally, I'm going to be able to do end-to-end learning. I'm going to be able to do detection and data association in one go. And I don't think it will come as a surprise to anyone that I'm going to use transformers or attention or graph neural networks, however you want to call them. And so we're going to do tracking by attention. So basically, attention is going to jointly solve the detection and the tracking tasks. So I'm going to present only one type of solution for this task. So while we were working on this paper, I think something like 4 or 5 similar papers appeared on arXiv. So it's not like we're the only ones that thought about this. So I'm going to present our solution but there are quite some similar solutions out there. They're all based on the same ideas, so I think you will get a good picture with our solution. So we were inspired, of course, by the work DETR, which uses transformers to perform detection. So I think this work is really cool because it poses the object detection problem in a kind of new way. So it poses it as a set prediction problem. So before in faster CNN or even YOLO, it was more a classification problem, right? So I'm going to take a bounding box and I'm going to classify it. Is this an object or not? Is this a car or a person? But this is really a set prediction problem. So I'm going to output the number of bounding boxes that I need, and I'm going to say whether this is a person or background or whatever we need. For this, we have a couple of interesting ingredients. So we have the transformer encoder that takes in the image and essentially extract the necessary features. But of course, the interesting part is on the decoder, right? So this decoder is going to use self-attention to decode what they call object queries. So object queries are nothing else than vectors, a learned vector that you're going to initialize with some random number, and later on is going to morph into something useful to extract bounding boxes. Whatever that is, it's something that is learned, it's just a vector. Let's say we have 128 values in there. And this vector is going to morph into bounding boxes thanks to the decoder. Okay, so let's look at how can we actually extend this to perform tracking, right? So in the first frame, we do exactly the same thing as DETR, right? So we have our image, we encode this image with the CNN and the transformer encoder, and we pass it on to the decoder. And all the magic happens there, where we have our object queries, which are these 128 vectors. They pass through the decoder, and they get converted into boxes. In this case, we have 3 boxes, the red, the green, and the blue. And the output is basically through an MLP that tells you the coordinate of the box, the class of the box. And the only thing that the decoder does, again, is transform these object queries into these boxes. So this is the first frame, right? We start with these 3 boxes in our first frame. And now the idea is that we have to transform these 3 boxes into their new locations in the second frame. So of course, if we now continue applying DETR, we will not have this association between boxes. So we need to have some flow of information from the first frame to the second frame. And this happens through this connection that I've drawn here. And this means that we're going to have the output of the previous frame before the MLP that predicts the boxes. These object queries have been transformed into something, into another vector. And this vector is what we're going to concatenate in the next frame. And this we call track queries, because now we do have a notion of an identity in there, right? It's not an object query that can decode any object, but it's a track query that hopefully will decode the exact object that it has been following in the previous frame. So this is why these track objects have colors. You can see below that we have these 3 track queries, the red, the green, and the blue, because they already have an identity attached to them. And now the idea is very simple. I'm going to pass all these track queries and object queries through the decoder, and it's going to decode new boxes. But now, whatever box the red track query decodes is going to be the red box. I'm just going to assign the identity in there. So automatically, what I have is kind of like what we did with Tractor, right? I have a relationship between red boxes just because the red track query decoded that box. So imagine all the information that has to go into these track queries. So here we can have the motion model embedded in here. We can have an appearance model embedded in here. So any information that the decoder needs to decode the box has to be encoded in the track query, and has to be encoded automatically, of course. So of course, in this second frame, I also have, for example, the purple box, which has appeared new, right? It's a new detection. It has been decoded from an object query, and therefore we have a new trajectory starting. And in the third frame, I will have the example where I have the blue query, the blue track query, it's not decoding any box, and this means that the trajectory has ended. Right, so starting a trajectory and ending a trajectory is actually very natural, right? Whether the track query decodes a box or not, whether an object query decodes a new box or not. So this is like a very natural way of starting and ending trajectories. So let's see a little bit more how this transformer actually works, and especially which elements of this transformer are actually useful for tracking, right? I mean, I'm not going to go into the architecture, but I do want to give an idea of what each type of element in this encoder-decoder transformer, what each element is actually doing for the task of tracking. So, okay, the first part is obvious, right? I mean, we have to encode the image features. There is no secret in there. Then I'm going to have this concatenation of object and track queries. So here what I'm doing is I'm putting at the same level the object queries and the track queries. I'm treating them exactly in the same way. And then I have this encoder-decoder with two types of attention, self-attention and encoder-decoder attention. Now, in the last step, as I said, we need to morph these queries into something that we can interpret. And in this case, we have a couple of MLPs that transform it into bounding box coordinates and the class of the object. Now let's go for the interesting part, right? This self-attention and encoder-decoder attention. Why do we need these two elements? And what is this actually doing for the tracking task? So let's look at actually how do we do query decoding. So query decoding is going to happen with these two types of attention, as I've said, the self-attention between queries and the encoder-decoder attention. So self-attention between queries, I've said before that I'm concatenating track queries and object queries, which means that they are all put together into the same bucket. And so when I have self-attention between queries, I'm letting my object queries talk to my track queries. So if I have, for example, to initialize a new track, right? So an object query has to decode a new box. It's going to look at the track queries and it's going to say, does any of these track queries represent this pedestrian that I want to initialize? And the track queries are maybe focusing on other pedestrians. So the object query says, okay, then I'm going to take this pedestrian and I'm going to put a box in there. Like, for example, here we have the purple box that is initialized from an object query. This object query needs to make sure that no other track query is following that box. So track queries are going to have an implicit priority when we're talking about decoding boxes. And of course, the same happens when we need to terminate an occluded track, right? So we have the blue query that doesn't know where the pedestrian is, doesn't want to decode a box. It's useful to look at where the other boxes are decoding to see, well, maybe there is a person-to-person occlusion, right? So if the red box is maybe occluding my pedestrian or where I think my pedestrian should be, then it makes sense that I don't put out any box, just not to make any mistake. So this is where the self-attention between queries helps. Now let's go for the encoder-decoder attention. So here, it's going to be useful because I'm going to grab features from the image. And of course, I need this to find a new object in the frame, right? I need to look at image features and say, yes, this looks like a person. And at the same time, adjust to the change position of the tracks, right? The persons are moving, and I need to keep moving this bounding box. And if you're familiar with Detter, you might know that these object queries are kind of location bounded, right? So there's an object query that is responsible for firing boxes on the bottom left corner of the image, which means there is a notion of location embedded into these queries. And so what we need is we need the image information to change these locations, right? The track queries need to update the location as the object is moving. Okay, so another important question, right? I mean, can we actually recover from occlusions with this method? Because anything that I've been describing so far is about frame-by-frame tracking, right? And I said that if there is, for example, the blue track query cannot find the pedestrian that was tracking until then, it's going to output no box. So it's going to stop the trajectory. So how can I actually recover from occlusions with this method? Well, super simple. I'm just going to keep my track queries active for a period of time. So the only thing that I need to do is that even if the track query doesn't output any box in this frame, I just still keep it active for a number of frames. And if at some point the person reappears, then it's going to fire again. So super simple way of recovering from occlusions. We don't need any extra re-ID head on top, which is what pretty much all trackers do. We hope that the re-ID information is embedded into these track queries. But the bad thing is that the spatial information that it is embedded into the track queries, as I've said before, it kind of prevents the application to long-term occlusions, right? So if I'm walking around the scene, there is this big occlusion, and I appear on the other side of the image, then my track query will still be looking for me on the first part of the image. So if the pedestrian has really moved a lot, then it is very likely that the track query cannot follow it. So this is the only bad thing about this method, and we really try to solve this problem, but there is really not enough data to train a transformer to solve also this problem. So at some point, it becomes a problem of data, right? You don't have enough instances of these very particular problems so that you can train your transformer properly. So just as a summary, so I think like TrackFormer is really an elegant formulation to tracking, right? It sort of naturally merges this concept of detection, the concept of data association. It embeds inside re-ID, motion model, anything that the track query needs to track the object is going to be learned automatically. So I think this is really cool. It does have really good performance with partial occlusions. And of course, good performance where other detectors are weak, because now you're looking at some temporal window. So if there's not a lot of image evidence that a person is there, but you were tracking a person in that area, then you're going to fire a detection also in that particular frame. And we do get state-of-the-art results. I have to say, this was the worst method to train. It's so painful to train transformers. It's really, really painful. We had to do tons of tricks. We had to do tons of data augmentations. So really take a look at your data. Really take a look at the failure methods when you're training transformer, because it's, of course, always a matter of data, right? A matter of how many instances of this particular problem you have. OK, so I went with this presentation from the first tracking by detection to tracking by regression, represented by tractor or by center track. And we showed in these two works that one can turn a detector into a tracker. So we can do much more with a detector than we thought initially. And I think the most important part of that work was to bring out the real tracking problems, right? To say, OK, we need to really work on occlusions. We need to work on crowded scenes, which is what we try to do with graph neural networks. And it was really good for partial occlusions. It was really good for crowds, but not really an end-to-end solution. And this is what I presented last with tracking by attention, in which detection and tracking were finally merged for this end-to-end learning solution. So this is cool, right? It seems like there has been a lot of progress in tracking. So now it's like, OK, what's next? So one problem is that is long occlusions, right? So I've said that with the graph neural networks, we couldn't solve long occlusions. With TrackFormer, we cannot solve long occlusions, especially if the person has moved a lot in the image. So long occlusions remain unsolved. Now, typical research into long occlusions, into recovering an identity of the person after this gap in detections, has been going pretty much in two directions. So the direction of re-identification, so as I said before, we have the appearance model of a person, and we're looking all over the image to see if that appearance reappears again in a future frame. And the other way of tackling this is trajectory prediction. So trying to really hallucinate how the person has moved in the 3D plane, and so where it will appear in the image next. So the first one, we are really working hard to make it work for long occlusions, but for crowded scenes, we have a lot of ambiguities, we have a lot of identities, they all look very similar. So it's hard to solve this problem only with an appearance model. And with trajectory prediction, we have another problem, and this is that you need 3D, right? You cannot really hallucinate trajectories of a pedestrian if you don't have any 3D information. It's just not going to be accurate. So these are two great directions, and these are kind of two subfields that spawned from the tracking community. But when you're looking at putting them back into the trackers, well, they are not really ready yet. So there's a lot of research that we need to do here. Okay, so for the last part of my talk, I would like to do something a bit more inspiring, right? So especially for young PhD students that are maybe, still looking for a topic to focus their research on, what do I think are inspiring next steps that we can do in MOD? What are the next big thing that we should be working on? So forget about tracking by detection, forget about tracking by attention. We can solve a lot of things already with these methods. What we cannot solve, though, is the open world, right? So any of the trackers that I've talked about are for objects that are really well known, for cars, for person, for cats. These are objects that we can detect and objects that we can track. That's not the real problem. The problem is when we go into the open world and we find objects that are just weird, right? For example, I don't know, you have a horse in front of your car. Maybe you have not trained your detector for horses, right? But suddenly, this object appears in front of your car and you have to do something. So open world video understanding is super interesting. We have already done a bit of work into that segment. But essentially, the idea would be to bring the whole concept of video understanding, so everything that we do in video, optical flow, tracking, all of these tasks, bring them to the open world. So essentially for classes for which we have 0 pre-trained detectors, classes which are weird. And so we had this work just this year. We're going to present it in a few months about open world tracking, in which we try to at least define this problem, right? Because open world tracking means that you're going to track any number of unknown objects, but you still want to do it in a systematic way, right? You still want to create a benchmark, you still want to evaluate methods, compare them to each other, but how do you create a benchmark which is by definition not open, but it's actually closed world? So how do you create a closed world benchmark for the open world problem? So this is what we kind of try to tackle here in this paper called Opening Up Open World Tracking. And the important thing is actually opening up, because it's not that we solve the problem, but we start talking about the problem, right? We start putting out there, okay, this is an interesting thing to be looking at. And if you check the graph here, so you will see MOD challenge that is actually tracking, so sorry, on the x-axis we have the number of classes that we want to deal with in tracking. And you see that the MOD challenge benchmark just has one class, right? Pedestrians. We're trying to track pedestrians. And these are all the classes that we're trying to target in open world. So really tons and tons of classes that we actually want to track. And the interesting part is the classes that are outside of the benchmark, what we call these unknown unknowns. So the classes for which we have 0 data for now, but at some point we will have data for in the future. So there's tons of problems that are interesting to work on, right? We can have retrieval. We can say, well, if I cannot estimate the class of the object, at least let me extract some motion attributes and let's try to figure out something from them. Of course, zero-shot learning, but not the zero-shot learning that you're used to, but the zero-shot learning in the wild without pre-localized objects, with multiple objects interacting with each other. Some are known, some are unknown. Of course, tons of semi-supervised learning to deal with all the amounts of unlabeled data. So these are all like super interesting problems that I think will come up in the future. And of course, we're also looking at increasing a little bit the accuracy of our annotations, right? So if we're going to do open world video understanding, we cannot focus on bounding boxes. Bounding boxes are good for classes which are known, but as soon as we go into the unknown, we need to have a bit more precise outputs, right? We need to say, yes, these pixels belong to an object that I don't know, but it's moving into this direction, for example. So for this, we worked on annotating mod challenge with much more precise annotations, so really pixel-wise annotations, so that we can basically do panoptic segmentation, but with a very high frame rate. Because usually we either have pixel accuracy or we have temporal density of annotations. And what we try to do is we try to have both, right? So really high density in the annotations in the spatial domain, but also in the temporal domain. And of course, the other problem is, okay, how do we actually obtain data, right? So obtaining data for the open world is a pain. It's already a pain for the closed world. But let's look at, for example, a class that we already know, right? So we're trying to track cars, and we suddenly get this image. This is not the typical image of cars that we have, even though it's very, very common. So even for known categories, right, we still need labels in various conditions. We need labels in sunny weather, we need labels in rainy weather. But now put this together with video tasks, right? This means that we not only need variation in appearance, but we also need variation in motion. So we now have another dimension for which we have to obtain more data. So it really becomes an explosion of data that we actually need to annotate if we really want to go out into the open world. And this is only for known classes. I'm not even talking about unknown classes. So what we have been working on with some groups here in Italy was working on synthetic data. So trying to leverage the very famous GTA game for people tracking and seeing a little bit how can we use this synthetic data to train detectors, trackers, and re-identification models for the specific task of person tracking, right? So how large is the domain gap for person tracking? And it turns out, of course, that synthetic data really helps. For trackers, the gap is not so big. For detectors, it's a little bit larger. So this is, I think, something that is very well known. But the question is, and I hope that, that people will come up with interesting solutions, is once you have this amount of synthetic data, what can you do in tracking, right? What can you do next in tracking? So I hope that this inspires people to work on this type of data. And I also hope that we can now go into the area of let's synthesize weird objects, right? And let's see what we can do with that type of data. Okay, so with this, I reached the end of my talk. So the first thing that I hope this presentation conveyed is that multi-object tracking is fun, right? So don't do like my student. It is really fun. It is really challenging. I think there's a lot of fun aspects about it. Of course, there's also the bad thing that maybe like my mom is like asking me, oh, but if you're tracking people, isn't this like surveillance type of thing? I mean, this is really bad, right? It's true that any methods can be used for good and for bad. I prefer to think that I'm going to save some people if I put my tracker into an autonomous driving car, rather than thinking that it's going to be used for surveillance, right? So we don't need any identifying information in our trackers. So we're also working on privatizing mod challenge, trying to make it anonymous, removing any identity information, and hopefully this will bring only the good aspects of multi-object tracking. Also, as you have seen, a lot of progress has been made, but still processing videos with end-to-end learning is challenging. It's very expensive. You have a lot of information. You have a lot of pixels to deal with. So really taking this to real time, well, we're not there yet, clearly. And also the lack of data that we have, the lack of unique cases is very problematic when you're relying only on end-to-end learning. So this is still something that we have to work on. And also, especially for the more junior people here, I think there's a huge opportunity in open world tracking. So I really hope that we have a lot of fresh minds with fresh ideas that are working on this problem, because I think this is going to be the next big thing, the next big fun thing to work on in multiple object tracking. So with this, I would like to thank especially the collaborators of the 3 main works that I presented here, especially my students Tim and Guillem, who really worked hard on these 3 papers. And of course, also all the other collaborators of the works that I've just briefly mentioned. And I would also like to thank you, especially for your attention. And if you have any questions, I hope that we can have a nice discussion. Thank you.
Thank you. Thank you, Laura, for this interesting speech. Any question in the audience? Yes.
Thank you. Thank you very much for your wonderful talk. One question is, I really love the chart in which you show the failure of, the bounding box which caused the most failure. So do you have any suggestion on how the latest proposal, the transformer-based one, compares with respect to the other? So did you manage to get your state-of-the-art by improving another little on the big ones, or you started solving for the, small ones? And then the second question is, when you were saying about training end-to-end from both the graph neural network and the CNN. So you mentioned that it was too hard to do 2 years ago, or 3 years ago, I can't remember. And then you moved to transformer, which is known to be, tough to train because, and it requires a lot of, powerful machines. So how, a rough figure, how harder it is to train the latest transformer, which is doing a lot of stuff? So thank you very much.
Okay, so thanks. These are wonderful questions. So for the first question, TrackFormer and also the graph neural network did tackle those middle cases well. With the graph, there's a small trick to it that my student will hate me for saying, but it's written in the paper, right? It's not like we hide it. But we do pre-process the bounding boxes with Tractor, and then we apply the graph on top, right? So with this, we are able to obtain a little bit better detections on those parts in the middle between this 25 and 75 visibility. And then we can further improve it with graph neural networks, right? So we are working in that range that I presented. As for the second question, so I would like to state very, like something that I think everyone knows, but it's not said enough, is that transformers are actually graph neural networks, right? So it's exactly the same thing, just that in transformers you have your batch normalization because you have multiple heads, you have to bring them into a common space to compare with each other, but essentially it is the same, just that graph neural networks are a more general formulation, right? So it's not that the graph neural network was easier to train than the transformer per se, but we already had detections, right? Which means that the whole problem is easier. Now, when we put TrackFormer, we put detection and data association into the mix. And this is what makes it really hard, right? And so why we couldn't do backpropagation back in the day all the way to the image was merely a matter of GPU memory, right? So then we bought 48 gigabyte GPUs, my students were happy, things could get trained, solved, right? So I think it was more of an engineering thing that one could have, saved the gradients and done something with that and so on. We didn't have time back in the day. When we actually tried it, it didn't improve things so much, I have to be honest, so that was a bit sad. But I think the difficulty of training TrackFormer is not really that. It's really that when you're doing tracking and association at the same time, you really need to find a lot of data that represents each particular case, right? So that represents this type of occlusion, that represents this type of appearance of an object, how the objects move. And so this is just an explosion of data, right? So we did, for example, a lot of tricks on augmenting false positive, so creating artificially false positives, because there were not enough in the data. And so TrackFormer was creating a lot of false positives, right? So I mean, these type of things were what made it kind of hard to train, or at least it took us quite a long time to achieve a good performance.
Vittorio?
Okay, thank you. Thanks, Laura, for a very interesting talk. So my question is more about your final discussion about this open world video understanding or tracking. So you know about the works in which we are making object detection where object is not a particular class, but anyway, objects, generic objects. There are a few works now. I would like to ask you your opinion about the fact that if you want to go really to open world, I think we have to, in a way, address some unsupervised or self-supervised learning case, because I think it's impossible to, in a way, annotate everything, as you said, also in these cases in which you have to, in a way, try to model all the possible situations in which a tracker can deal with. So what about your opinion to do some this video understanding, open world and or tracking without annotation? Of course, one answer is if you go to synthetic sim to real, it's one possibility. But what about going really towards unsupervised or self-supervised learning for solving tracking?
Mm-hmm. So indeed, this is one of the main directions, right, for starting to tackle open world tracking. So for our baseline, we actually use class agnostic detectors as a starting point. And then we showed, okay, how do we extend this to tracking, create some baselines, start to, study the field, right? That was what we did in the paper. But I think that when you have a single image and you're trying to do detection of a weird object, it's not the same as if you have a video, right? In video, you have potentially the object moving. And so even with the motion, you should be able to infer a lot of things, right? Even with classic optical flow plus some clustering to extract the objects, you should be able to do something, right? So that's why I think that having videos and doing open world video understanding is different from doing class agnostic detections, right? But of course, yeah, you will not have labels, or you will have a few labels from synthetic data, maybe, if you're lucky. You're going to have to generalize to the real world, and this is all going to happen with semi-supervised learning or with some domain adaptation, maybe. But definitely, these are things that we have not really studied much in video, I think. So the whole idea of doing semi-supervised learning with a temporal domain is something that only very few works do. And I think this will be a nice key to unlock open world video understanding.
Thank you for your presentation, very nice presentation. First, I would like to know just a detail about the time. You said that you record some kind of time in the query when the occlusion appears and when the object appears again. Have you any indicator, or you're based on the experience, how much you wait for the object to reappear?
So you mean the time window that we have between the appearance and the disappearance and the appearance?
Yes.
I think we had something like 50 or 100 frames. We changed it because first we had like a very small window because it was not working. Then we tried larger and larger windows that it was better trained. So I think the problem is not only the time window, but actually how the object has moved, right? So if I'm standing here and there's occlusions because there's people passing around, and then suddenly there's no more people and I reappear, but I'm still at the same position, I think this is not a huge problem, right? If I move around behind an occlusion and I reappear on the other side, then this is a problem. Then the track query has this notion of, the object should be in this part of the image, and when I reappear on the other side, it's not strong enough to jump So the appearance model, at least that's the intuition, right? I mean, this is something that one cannot really know. But the intuition is that the appearance model is not really strong enough to track all around the image. So for this, we should really do a re-ID type of training, like a lot of data augmentation to put boxes all around the image and try to track them. But then, yeah, then I think you're losing the whole motion model aspect. So you really have to balance both in this unique track query, right?
Thank you.
Laura, super presentation. Thanks a lot. Just a question about something you mentioned for a bit, the problem of 3D. So how can we deal with, in general, we don't deal with, there is Google, I try to answer my phone. In general, people don't take care about 3D because we don't have annotated data in 3D. So we cannot do a supervised learning on that. But I still believe that even if you have some information about the perspective or about everything, especially when you go in the direction of open world, it could be a new cue, very important. Can you give your idea of that?
Yeah. So definitely, like when I started collaborating with Argo, which is this autonomous driving, well, was a startup. Now it's quite a big company. They were like, no, look, we're not interested in 2D. What are you doing, right? I mean, we have lidars, we have stereo, we have really nice 3D. And so they do everything in 3D, right? So it is true that this is a kind of a specific case, right? Mod Challenge doing 2D tracking is kind of a specific case. Anything that in the real world we do in autonomous driving or in augmented reality is 3D, right? And there, of course, there are different problems. But I think the whole, for example, ambiguity of people crossing in front of one another, this is completely gone, right? Because you know who's in front, you know who's in the back. So many problems become simpler, but doing end-to-end learning with 3D data is expensive. It's also not really clear which architecture should you use, right? So there's a lot of research still going on there. When you put temporal information on top, then it's over, right? Like 4D, fit it all into a network, it's over. So I think you have different problems and problems that we will for sure tackle, but you have the advantages of having more clear data. So it's a bit of a pro and con, to be honest. So what we have been trying to do with Mod Challenge was to lift the 2D detections into some pseudo 3D with some predictive depth. So there you can already work on trajectory prediction. You can already infer some trajectory, especially close to the camera. But it's a kind of 2.5D, right? It's not really something that will solve the problem. And I don't think we should be even tackling these too much because we do have 3D sensors and we will use them in the future. So I think definitely that we should move towards 3D at some point in the very near future of Mod Challenge.
Okay, thank you. We are running out of time and we need to shift to the other session. But before that, let's thank once again our keynote speaker.
Okay. Hello again. So we're going into the oral session 5. We will have a session on pattern recognition and machine learning. We have 4 speakers for this session. So the first speaker is going to be remote, is going to be Xin Huang about landmark-guided conditional GANs for face aging.
Hi. Hi everyone, can you hear me? Hello? Okay.
Sì, rispondetele dal microfono, per favore.
Okay. Sorry, because I'm in the airport now, so I would play the recorded presentation here to avoid the noise. So.
No worries, we can hear you.
Okay.
Hi everyone, thank you for your interest in our work. My name is Xin Huang, and in this presentation, I will introduce our work, landmark-guided conditional GANs for face agent. So what is face agent? Given an input face image, the task of face age transformation is to generate the appearance of a person at different ages. Such face transformation is on demand because of its potential use, such as mission child rendering, commercial products like interesting apps, movie production, and so on. Basically, there are 2 strategies of face age transformation. Some researchers propose sequence-based methods use chain frameworks. Each unit can be developed as a recurrent neural network with the advantages of memorizing the earlier unit states. This kind of methods perform the group-based learning. It requires the true age of testing phase to localize the transition state, so it might not be convenient. In addition, these approaches only provide age progression from younger phase to older ones. So if you want to achieve flexible bidirectional phase age changes, we may need to retrain the model inversely. Condition-based models are established on conditional GANs. Age labels are encoded in one halt encoded manner. The number of input condition channels corresponds to the number of age groups. To achieve reliable transformation, models should maintain input identity details, introduce target age characteristics, and finally generate natural-looking face images. Some of the recent networks can do face regression very well. However, these transformed images still contain some limitations like poor age or poor identity consistency and lack of changes in facial structures between very young and very old age. Because during early years, like from birth to teenager, a person's head shape and eye location change dramatically. To solve these problems, we develop a novel symmetric network. The generator is conditioned with external landmark attention, which can help to generate face with more reasonable facial structures. This is the pipeline of our proposed LGC GAN for face agent. The black flowchart shows the primal CGAN and the red flowchart shows the dual CGAN. Given multiple set of training face images with n different ages, not necessarily to be the same person. Our goal is to learn a face agent model GF and a face reconstruction model GR. Then give any facial image and target age condition. This model GF can predict face of a person at different ages, but still preserve the personalized features of the original face. Specifically, our model first transforms a face image to other ages based on age conditions, and then learn to invert the task. The external landmark attention is applied in the generator, which can emphasize the location and shapes of the face features. Our framework also considers age-related region and age-unrelated region separately through an internal attention content mask. This helps to focus on applying transformation on age-related region. Besides, the ghost artifacts between age and age groups can be significantly reduced. The definition of loss function L is critical for the performance of our network. It is composed of 4 parts. Adversarial loss for matching the distribution of outputs to the data distribution. Each classification module is used to further guarantee the generated phases fall into the target age group. We pre-train an age classifier and use it to identify which age group the phase comes from. The third is identity loss. It is important to preserve the identity information for the synthesized image, face image. However, this adversarial loss only makes the generator generate samples that follow the target data distribution. Consequently, the generated samples can be like any person in the target age group. So adversarial loss and age classification loss cannot guarantee that the generated samples can preserve the identity information. So to keep the identity information for the generated images, we introduce a perceptual loss into our phase agent objective to shorten the distance between input and output images in the same lower feature space. The cycle consistency loss can be used to enforce forward and backward consistency. If a phase generated by SIGAN preserves a person's identity well and is consistent with target age group, then the reconstruction step, the phase the network should transform the aging result back to the input image. We assume that the distance between current landmarks and example landmarks in feature space. Here is a attention map. Attention map 1. This can represent the distance between current image and the example image in image feature space. Based on this assumption, we can obtain current image feature HI through channel-wise concatenation by feeding the computed new features and attention map 2, along with the image feature SD into following upsampling layers, we obtain the current image feature HK. This will be used to generate an attention map FA and a content map FC by applying convolution and activation operations on HK. This step enforces the network to focus on those regions of the image that are relevant to phase agent and keeps the background information unchanged, and so preserve the identity consistency. So how we show the effect of facial landmark prediction? For the 2 input phases, their facial landmarks are retrieved by 2D phase alignment. Changes to this landmark locations are predicted for different age groups, which guide the synthesized phase to follow. So the external landmark attention contributes to the accuracy. In our experiments, UTK phase is used. UTK phase is a large-scale phase data set with long age span, range from 0 to 116 years old. We divide the images into 10 age groups, so we can use a 10-dimension one-hot vector to present the age condition. It's significant that our dataset doesn't contain multiple images for each person, which cover different age groups. It means that our training dataset is unpaired and non-sequential. For the generated results, we can see that our model performs wide range age transformation and produce natural-looking faces. We already know that it's a great challenge to transform face between very young and to very old ages. Here is an example. If we have a 90 years old face and want to produce her face in her childhood, our model can produce back to her child age with big eyes, round facial shapes, and the face generated by IPC GAN only have less wrinkles, but the facial features doesn't have difference with the source example image. But if we have a child face and want to generate his face in his 80s, our model produces a face with droopy eyes and thin cheeks. We use aging accuracy and identity verification to evaluate the generation accuracy in terms of aging effect and whether the identity of a person has been properly preserved. The above two tests show that ITC GAN is good at preserving identity information but lacks ability of generating aging faces with accurate target age appearance. CAE perform better than ITC GAN in age accuracy but fails to preserve personal identity. Our LGC GAN consistently outperforms the two models in both evaluation metrics. In conclusion, we developed a novel landmark-guided conditional GANs for face agent. We first introduced external landmark attention and built-in attention to the generator to focus aging effects at important regions. A dual learning framework is also used to both generation aging results and generate aging result and reconstruct the input photos. By minimizing the multiple loss terms, our model can learn the transition pattern at different ages and perform well in preserving personal identity. Both qualitative and quantitative experiments validates the effectiveness of our approaches and its advantages over the existing ones. Thank you for your listening. This is my presentation.
Thank you for the presentation. Are there any questions? So I might start with a question. So you presented these like 4 losses. Did you analyze like which one was more important, which one was actually creating each of the effects so that you have an idea like what is driving the result?
Hi. Yes, because we use the parameters to balance the different losses. And sorry for the noise because I'm in the airport, and we set the different weight of different losses by experiments, like the forward and the backward we set to the same one, and we set the generation loss as a very important loss. So there are no very standard method to set which one is more important. These are all based on our experience. Sorry.
Thank you. Are there any further questions? No? Okay, then thank you so much for your presentation.
Thank you. Thank you.
Okay, so we will move to the second speaker, Nicola Messina. So he's going to talk about recurrent vision transformer for solving visual reasoning problems.
Okay, nice. Okay, hi there, everyone. I'm Nicola Messina, and I'm from the Institute of Information Science and Technology from the CNR in Pisa. And I'm glad to present you this work on recurrent vision transformer for solving visual reasoning problems. I would like to thank the co-authors of this work, Giuseppe Amato, Fabio Carrara, Claudio Gennaro, and Fabrizio Falchi. So a brief overview of this work. The aim is to challenge deep neural networks, and in particular in this work, a particular kind of transformer network with abstract reasoning problems requiring spatial comparisons. And in particular, we considered this kind of tasks that is called same different tasks, that consist in understanding if two shapes in an image are the same or not under different challenging geometrical transformations. The motivation of this work is that we want to understand spatial and abstract reasoning abilities of deep neural networks. And we have to consider that humans can solve these problems in very few shots and almost perfectly, while deep neural networks has been shown to struggle. And also, we have found some interesting long-term downstream applications. For example, in the image on the top right, we can, for example, imagine that we want to understand symmetries in art or architecture, for example, quantifying beauty in cultural heritage, for example. Or, for example, in another modality, for example, in music, in song detection and understanding, we could use these tools for finding repeating structures in a song, for example, high-level musical understanding or musical retrieval. So in this work, we tackled actually a visual reasoning test, and we used this kind of dataset that is called Synthetic Visual Reasoning Test Dataset, or SVRT. And it is made of simple 2D, of images containing simple 2D closed curves. And this dataset contains actually 23 different subtasks. And the most challenging ones, according to Kemetal, are comparisons problem. Here we have these 4 problems in 4 different columns with negative example and positive example for each of the tasks. In this case, we have the number 1 that consists in, the problem number 1 consists in understanding if there are 2 shapes that are only translated in the image. The number 5 consists in understanding if there are 2 pairs of translated shapes. The number 20 that consists in understanding if there are 2 shapes that are the same, but they are translated and flipped along an unknown symmetry axis. And the number 21 that consists in understanding is actually the most challenging one, consists in understanding if there are 2 shapes that are the same, but scaled, rotated, and translated. Actually, as you may imagine, all these problems can be tackled as binary classification problems. So we have an input image, we have some sort of feature extraction module that outputs some sort of vectorial representation that can be mapped into a one-dimensional space and converted into a probability distribution that basically outputs if the 2 shapes in the image are the same. So all boils down to understanding and finding a suitable architecture for our feature extraction module. So as you all may know, and I mean this is tackled a lot in these days at ECHAP, vision transformers are revolutionizing computer vision. And they basically were able to achieve very competitive and actually state-of-the-art performances on one of the main tasks of computer vision, that is image classification, without using any sort of convolution. They basically split the image into a set of non-overlapping patches, and they basically project the pixel space of each one of these patches using linear projection to a lower dimensional space to obtain basically a lower dimensional tokens that are then fed to the transformer encoder module that uses the output CLS to predict a probability distribution over the target classes. So basically, in principle, we can use this module, the vision transformer, for tackling our binary classification problem on the SVRT tasks. However, we have some major drawbacks. In fact, although transformers can capture non-local interactions, even after the first layer, given that they have infinite receptive field, actually they cannot perceive very well low-level patterns, and this is a problem. This is actually instead a way is the convolutional neural networks cannot directly spot non-local relationships. However, instead, they are quite good at finding edges and shapes. So this motivates us to use an hybrid architecture where instead of using linear projection for basically obtaining a vectorial representation from the patches, we used the final feature maps from a shallower convolutional neural network. So, but before diving into the actual proposed architecture, we miss an important ingredient, that is recurrent connections. In fact, there is the evidence in literature that recurrent connections have a role in reasoning. And recurrent connections, in fact, at an high level, from an high-level point of view, model iterative constructs that are key features in programming languages. So, for example, CornetS is a biologically inspired convolutional neural network with recurrent connections among some of its convolutional blocks. And it obtained good results on BrainScore, that is a composite benchmark for comparing models to the human brain. And also another field in literature developed memory-augmented neural networks that use recurrent networks to read and write on a working memory, and they are able to solve very simple programming tasks. So driven by all these concerns, we proposed this architecture, that is the recurrent width architecture, or better, a convolutional recurrent vision transformer architecture that basically extracts the features from an image using a shallow convolutional neural network that plays the role of perception network. And then there is an iterative recurrent transformer that basically iteratively refine the internal state that is composed by a lot of different vectors, one for each image patch, for refining the prediction. So recurrent connections implement iterative reasoning, basically, and they have the nice property of regularized model. In fact, we have a lot less free parameters, given that the parameters are shared, the parameters of the transformer encoder layer are shared among the different time steps. And also the recurrent connections, of course, refine the internal representation at each time step for obtaining a stable prediction. Also, we probed with an equivariant convolutional neural network as our shallow convolutional neural network that is actually equivariant to rotations and reflection, and this can be helpful for example, the problem 20 and problem 21 that are characterized by very hard geometrical transformations. The whole architecture is trained by enforcing a binary cross-entropy loss from the output tokens, from the CLS tokens in output from each of the time steps. And basically then we aggregate all these losses by averaging them for obtaining the final loss so that the model can be trained end-to-end. So this is the inference protocol. Actually, the most confident time step is used to predict the final result. So as of now, no probabilistic dynamic Elting mechanisms are used as in neural Turing machines or in the universal transformers. So we basically run the inference for a finite number of time steps, and then we take the time step t-bar for which we have the maximum likelihood. So for example, in this example, 0.79. So we have some results. So we can see that on two data regimes, so with 400K trained sample and 28K trained samples, our two versions, smaller and larger versions of our recurrent vision transformer can achieve very good results while in the meanwhile obtaining, using the lowest possible number of free parameters. And with respect to the other convolutional neural network trained by previous works. Notably, we can notice that neither the relation network and the vision transformers can converge on this task, and this is quite strange given that they are designed to acquire distant relationships between distant patches in an image. Also, given that we use transformer encoder, we can actually visualize the attention given a query image that is a query patch, sorry, that is actually represented by the red dot on the left image of each pair of images. And so we can inspect what the architecture is actually focusing on for actually predicting a result. So we have also performed some ablation studies. In particular, we studied the role of recurrent connections and equivariant convolutions. In particular, from the second row of the table, we can see that recurrent connections are critical. In fact, whenever we had the recurrent connections, we obtain almost perfection on problem 1 and problem 5. And also, equivariant, the use of equivariant convolutions improves accuracy in problem 20 and problem 21 that involve complex geometrical transformation, and this is actually an interesting result and overall unexpected result. And also, we can also visualize the attention at the successive time steps. So we can notice that initially the attention maps are very noisy, but they then are refined at the successive time steps at inference time. So in conclusions, we introduced the recurrent VIT architecture for solving the most challenging SVRT tasks. And we showed that the convolutional extractor and together with the recurrent connections play an important role in solving these tasks. And we obtained the best results in terms of accuracy and model complexity with respect to state-of-the-art convolutional neural networks. And future works include applying this research to more complex scenarios and also the real-world scenarios I was mentioning in the introduction, and also exploring some smart dynamic healthy mechanisms for automatically and probabilistically understand when it is time to stop during the inference phase. So thank you very much. This is my contact email, and I leave you with the QR code with our code on GitHub for reproducing our results. Thank you very much for your attention.
Are there any questions? Okay, so maybe I'll start with a question. So from the results, like, did I understand correctly that the first two rows, so there are all these 50s grayed out? These are not real results?
Actually, we performed the training multiple times. So actually, we obtain every time a little different result than computing then the mean basically converged to a fully random toss. So basically, this architecture are not in any way able to converge and to discriminate in any case the same from the different case.
Okay, I see. Okay. So do you think this could be because also you don't have so many training samples? I see here like 400,000 or 28,000. This might be too small for transformers, right?
Yes, exactly. So this is one of the reasons for which we decided to compress the architecture and to induce some inductive biases that in the vision transformer plane architecture are not present. So we basically added we entangled the weights also in time so that we had the lowest possible number of free parameters. And doing so, however, we obtain very, very good results. So this means that the architecture is able to generalize without any chance of overfitting, basically.
Okay, but you say you're doing two things, right? You have the CNN with the inductive bias and then the recurrent part. So which is the crucial one to obtain these results?
So actually, without the I think, actually, I don't know, I don't remember if we made this experiment, but for sure, having the convolution neural networks, this helps a lot. And also, if you, this has some evidences also in other tasks. For example, the image classification itself, in fact, on Kaggle, for example, sorry, not on Kaggle, but on the leaderboard of image classification problems, of the image classification problem, basically the top architectures are hybrid architectures that use a convolutional network for extracting the patches, and then they use a transformer for reasoning on the relationships between those patches. So I think this is the idea behind this work and why it actually works.
Okay, thank you. Any further questions from the audience? Okay, if not, we thank the speaker again.
Thank you.
So the next speaker is Charalampos Davalas. He will talk about computationally efficient rehearsal for online continual learning.
Se può mettere a full screen, please, so we may make it on the video wall. Ah.
Thank you. My name is Charalampos Davalas from Harokopi University. I'm a PhD candidate, and my work is on continual learning with rehearsal methods and how we can make them more efficient. For start, what is continual learning? We start from one classification task, such as training between cats and dogs, and then we go on to a different task, let's say other different kinds of animals, and the final objective is to learn all tasks in the end, and so that our model, let's say a convolutional network, can classify all data from all classes. Of course, we also have to consider the online learning part, on which the tasks are not always whole. We have them in batches, so the model can only see small batches, and in some occasions we have some abrupt changes. Our stream feed might not have the exact same images. In our case, we tested the most aggressive scenario of abrupt changes. In all occasions, our basic problem is catastrophic forgetting. When we teach a model one task, it learns it as fast and efficient as possible. But when we go to task 2, it also does exactly the same thing. The problem is that now the model is more biased, and therefore mistakes will certainly happen. Here we will suggest, here are our suggestions for the problem. For starters, we prefer rehearsal methods in order to deal with catastrophic forgetting because they are very easy to implement. They are very simple. You just keep a small part of data, we merge them with new ones, and then you can mitigate a significant part of catastrophic forgetting. The problem is that they are very memory reliant. You actually are based on the buffer of old images. And then sometimes it might be not accustomed exactly to the model in use. Sometimes the model could be fine. Some others might have drastically changed, and it's not easy to know. So our suggestions are based on two questions. When do we have to train? We don't have always to train. We don't know exactly because a stream of data is very fast. We cannot know which image the model can see. So we need to know when to do so, when the model has a problem. The second part is how we train. Okay, we can see we need to train, there's a problem. What can we do about it? What exactly can we do about it? Because using the whole data set, the whole buffer and the whole stream images is impossible. For the one part, we use a drift detector. A drift detector actually is a sort of a statistical model which is based on misclassification rate. It says, well, I can classify these images correctly, and now I don't. And this change in concept, actually, shows us that the images have changed. Now the model is prone to catastrophic forgetting. We need to take action as fast as possible. And the other part is how to train. We have various ways to train when we find out when we find out that we need training. Some of our suggestions are rehearsal step calculator, actually repeating the same mini-batch training depending on misclassification rate. The second part is train as much as we need in order to converge to a solution. And also another part is using a learning rate schedule based on the model's needs. And all of these techniques can be combined to have various methodologies which can fit very well on different scenarios. Here we'll present our test and results. We use the CIFAR10 dataset, and we create a stream with the images in CIFAR10. And we also use a ResNet32 model in order to be able to be compared with baseline methods, which also has been trained with, we have done a small warm-up, because in real life we wouldn't just throw a model without any kind of knowledge. Well, our baseline is actually something called experience replay. We refer to it as CONR, constant rehearsal, because we made some small customizations in order to test various scenarios. We keep the same idea, though. CONR 1 is, well, I am on a stream, a new data is coming, we keep the old, and then we merge them and make one iteration step, one train with two batches, actually. We can do it also with n steps. Our suggestions for this specific example are a combination, are drift add-in, which is actually the drift activated version with our step calculator based on classification rate, and two drift-conf, which has two drift detectors, one with older data, one with new, and we train as much as we need to converge to a solution. Our metrics are actually based on average accuracy for all tasks, current task accuracy, how well the model can perform in task A when task A is there, and online accuracy, the latest batch, doesn't matter which task. We also keep the number of iterations in check because that's one of the most important things to make it as computationally efficient as possible. Here we see the current task accuracy. In fact, these sudden drops are because we change abruptly. This is a very aggressive scenario. What we mostly need to see is how well can the model react depending on how can the model react and repair its issues with catastrophic forgetting, and how much steps does it need. Our, for example, CONR 50 is probably a little better, but the problem is that the computations required are really almost impossible, while our suggestions in red and green lines, so that we can achieve similar results with almost half of the computations and even less. Also, our the time needed to repair these issues is far less. I think we actually can recover in some cases better. Here are the average results, which showcase better what we're trying to say. If you see driftadin and do driftconf use far less iterations, NT, and they can achieve almost identical average results on task accuracy and online accuracy. And these are conclusions. We can actually achieve almost identical results with far less computations. We can be more accurate in terms of dealing with the model's needs during in an online scenario as well. Thank you for your time. I'm waiting for your questions. Thank you.
Right, any questions from the audience? Come on, guys, don't make me ask all the questions. Okay, so I will start.
Classes, they are non-overlapping. This is a very aggressive scenario, actually. And yeah, we actually do that. We actually split the data set in a non-overlapping task, and each task has 2 classes.
Okay, and what would be like an application of this very aggressive scenario?
Yes, well, this is a very aggressive scenario. We mostly have to do it to be compared with baseline methods. In reality, it doesn't have to be so aggressive. We just make it strict so we can see the worst case scenario. In reality, changes are not that. In real life, well, for example, someone drives along the street, it's not one class of traffic sign and suddenly everything changes and you only see one type of traffic sign. There are abrupt changes and they are gradual. We tested the worst case scenario so we can be more confident about more realistic scenarios.
Okay, thank you. Oh, there's a question. Should I go there? Or? Yeah, okay. Oh, she comes with that.
So such a retraining step, how much of the data do you keep around of your previous steps?
Yes, very good question. Well, we keep a very small part. We keep, well, it depends on the location of the data set. I mean, if the data set is not that complex, we keep a very small part. We might keep 10% or even less. We actually try, this is also a part of our researching. We're using herding selection as well. It's not exactly standard for every data set. For CIFAR-10, we used we checked also about 50 images per class, 500 images per class, so we can see the interactions. It's not written in stone.
And so also for the drift detector, you're also using some of your old data to do kind of validation steps? So
yeah, we can actually use old and new data. There's no limitation to that. So we can test if the model is doing well in old data. If it has any problem with new data, it's actually more of a safeguard.
So then you have 2 sets of data you keep around of your old classes?
No. We keep a small buffer of old classes and the new data just pass along. You don't have to save new data. The drift detector is actually like a function. It's not, you don't have to keep.
Okay, you don't keep it. But for the drift detector, you still have to compare and look. Ali, how does the drift detector work?
The drift detector actually, what it does, it keeps the modeler's answers and keeps the labels of the images, the truth, because it's supervised learning. This is an application of supervised learning. We take the misclassification rate. the model can check, well, how much off it is. And then it decides, look, this is enough, you have to send the alarm, you have to repair the model.
Okay, thank you.
Thank you.
All right, if there are no more questions, thank you for the presentation.
Thank you. Thank you.
So our fourth and last speaker is going to be remote. So it's Yasser Boutaleb. He's going to present metric learning-based unsupervised domain adaptation for 3D skeleton hand activities categorization.
Hello, I'm Yasser Boutaleb. I'm a PhD student at the Institute of Research and Technology BICOM and École Centrale Chipilec from France. Today, I will present our method of metric learning-based unsupervised domain adaptation for 3D skeleton hand activities categorization. So the addressed main problem in this study is how to adapt a learning model based on a public dataset to another domain, for example, Industry 4.0. The solution that we propose is to first train an activity recognition model to classify activities based on labeled samples of a source domain, and then we try to map unlabeled activities of the target domain into low-dimensional and highly discriminated feature space that facilitate the clustering. At the end, as a result, we have clustered activities in distinct classes. And the question is how we can provide a best feature space clustering friendly. In the literature, we found two directions. The first direction is the generative neural networks, but the problem with this type of architecture is that they need a lot of data. The second direction is the deep metric learning loss functions, which is the direction that we have chosen in this work. In recent years, several penalty-based deep metric learning loss functions has been proposed. Those methods are mainly used to solve the face recognition problem, which try to map samples and impose discriminative constraints on the hypersphere manifold. So they modify the softmax logic by applying penalties in the angle or the cosine space. But manually assigned margin penalties, whether added on the angle or the cosine space, all improve the intra-class compactness and inter-class diversity in the feature space. And this is done by penalizing the target logic. However, it mainly depends on the manually assigned values of the margin and also the rescaling hyperparameters. The choice of those values relies on the data distribution and the dimension of the embedding space of the used neural network backbone. Here we give a general overview of the proposed method. So, for given labeled 3D hand activities, we train an activity recognition model equipped with our APML loss to learn a discriminative feature space. Then we use the trained neural network to map unlabeled activities into learned low-dimensional discriminative feature space. And then we apply a classical clustering to cluster similar activities, which result in pseudo-labels for those unlabeled samples. But during our experiments, we observed a high sensitivity of clustering algorithms regarding the feature space provided by the pre-trained model. To solve this problem, we repeated those two steps multiple times. This results in multi-predicted pseudo-labels. At the end, we apply a constant clustering on the set of predicted pseudo-labels, which result in a final pseudo-label for the unlabeled hand activities. Those function forces the neural network to learn a discriminated feature space. In contrast to the introduced state-of-the-art classes, we use the Euclidean distance between the feature vector z and the weight vector w of the last fully connected layer without any normalization to avoid the overfitting problem. Then we interpret this distance by a student t distribution with a single degree of freedom because it has the nice property of approximating the inverse law square for large pairwise distances. This makes the map's representation of joint probabilities almost invariant to changes in the map scale for embedded samples that are far apart, for example, the noisy samples. In contrast to the state-of-the-art losses that use softmax function to produce the probabilistic affinity score, we directly normalize the computed probabilities. We justify this by the fact that our target it's already based on a probability interpretation. So finally, our loss function is formulated in combination with the cross-entropy loss as follows. So the main aim of our loss function is to learn a discriminated feature space that facilitates the clustering and also keeping a good accuracy score for classification in source domain. And in contrast to state-of-the-art loss functions, it requires no additional hyperparameters. For example, the scale, the root scale parameters, or the margin. These two figures show a high sensitivity of clustering algorithms regarding the feature space provided by the pre-trained model over 100 repetitions. It's directly related to the random initialization of weights parameters, the dropout layers, and also the optimizer during the training process. To solve this problem, we repeated those two steps, the training and the clustering, multiple times. This results in a multi-predicted pseudo-labels that we pass into a conscious clustering process, which allow us to get the best prediction result among the 100 repetitions. For the experiment, we use the first-person hand action dataset, which provides 3D hand joint annotation, and it contains 3 different real-world scenarios: kitchen, office, and social. We used 2 different configurations to evaluate our method. So in the first configuration, we use the kitchen and the office scenarios as the source domain, and the social scenario as the target domain. In the second configuration, we used the kitchen and the social scenarios as source domain, while the office scenario is used as a target domain. So here we have some results. So in table 2 and 3, we show the impacts of our loss function on the clustering of the unlabeled hand activities compared with 4 state-of-the-art methods. We used 2 evaluation protocols. In table 2, we followed the first protocol with k the ground truth number of clusters not given. So for this, we use the affinity propagation clustering, which is evaluated using V-measure and adjusted mutual information matrix. In table 3, we followed the second protocol with providing k the ground truth number of clusters. For this protocol, we used agglomerative clustering, which is evaluated using unsupervised clustering accuracy. So as expected, the softmax loss performs very poorly against matricularing dedicated losses. And we observe that we outperforms at state-of-the-art losses in the first configuration, while we still equivalent in second configuration. Here, table 4 shows that our proposed loss function overcome allometric learning-based losses by more than 6% of accuracy, while it's still equivalent to softmax loss function for classification for activity and activity classification task on the source domain. So those results validate our APML loss function main contribution, which aims at balancing between learning a clustering-friendly manifold that facilitate the clustering of the embedded unilabeled samples of the target domain, and also ensuring a good recognition accuracy for the labeled ones in the source domain. Confusion matrix shows the high quality of clustering provided by our method. As you can see, most of the confused classes are meaningfully too close. For example, giveCoin and giveCard classes, where the performance action remains same, while only the objects card and coin change. We also observe a high confusion between post wine and poor wine classes, where the action change but the social activity context is still manifoldly close. So in this presentation, we have presented an application of user-supervised domain adaptation for unilateral 3D skeleton-based and activity clustering. And the experiments based on real-world dataset show that our feature space provided by our loss function allows good quality of clustering. And as a feature improvements, we plan to design a non-network architecture that provides clustering-friendly feature space while stabilizing the clustering sensitivity. Since our statistical and concise clustering strategy can be computationally expensive for some very complex deep network architecture or large amount of data.
So thank you for your attention. I hope it sounds good.
Yeah, it's good. Okay, are there any questions? Okay, if not, I will start with a question. So I did not quite get like an intuition behind your loss function. Can you give any intuition how it works or what does it represent?
So the loss function, or the proposed loss function, is the metric learning dedicated loss function. So it aims at learning a highly discriminative feature space that aims at improve the intra-class compactness of the clusters of the same of the features of the same class, and maximize the inter-class distance to separate the features of of different class. And the main things is that our loss function it learn this kind of discriminative feature space, and also it overcome the problem of overfitting and give good classification accuracy for the classification task. For example, here we give hand activity recognition, which is a classification of image sequences of activities.
So I've never seen this thing of actually using the weights in there. So do you mean like the last layer, or what type of weights are these?
Yes, in the last layer we use the weight of the last layer as the centers that attract embedded feature vectors to the corresponding class. So we use the weight of the last fully connected layer as a center weight, as a center of each class.
Okay, I see. Thank you. Okay, are there any further questions? If not, let's thank the speaker again.
Thank you.
So with this, we conclude the session on pattern recognition and machine learning, and I guess we can go to the coffee break.